So welcome back. So this week, we can finally start dealing with real numbers, since we spent the best part of the first 3 weeks building this kind of structure that would allow us to speak freely about what real numbers are, and make this intuitive notion that we've been using ever since Calc 1 a reality. So now we're no longer building everything upon a shaky ground, and such we can start now forgetting about what we did, which is a good thing now because we don't want to get stuck on this thing, but it is very important to start by doing so. And so remember, so we constructed R, so we have already constructed the real numbers R. And for now, remember that the construction we performed was something based on Dedekind cuts. There are other constructions that prove that there's an ordered field extending Q with all the needed operations. To provide the same kind of structure as the one we built. We did one based on Dedekind cuts. And the important thing now is that this R we constructed is a set containing Q, and second, the operations of addition and multiplication um, on Q extend to R, and in such a way that every element of R has an additive inverse. And also and this is very important, this was already true in Q, we needed to take out the zero element. So every non-zero element in R, yeah, so element of R has a multiplicative inverse. So what this means is that R is a field that preserves the field structure that Q already had, and Q is embedded into R. Okay, so R is a field in its own right, and it allows us to operate with Q inside it. And the operations are, of course, commutative, associative, and distributive property also holds. And such, I mean, all the usual standard algebraic operations that we've been used to performing in the past in algebra, in college algebra, and calculus and such, they're all valid, and I will not ask you to justify those things anymore. So whatever was true before this course, you can safely assume. There are some other properties that we need to stress now, but that's a part of the analysis, the actual analysis that goes into this class. But whatever you did before, however you added polynomials, that you added real numbers, multiply them, and the rules of deduction when you have, say, inequalities, they all apply. So, okay, also rules like um, apply without need for justification. So, okay, let me just rephrase that. So, there will be assumed be assumed to hold as as everyone use them in previous courses. Okay, so you no longer need to justify this kind of deductions. So when you multiply by a positive number, an inequality, then you keep the sign of the inequality. You don't need to do that anymore. Okay, so that's how things work. We did all of that. We went through all the trouble just to be able to forget and recover what we already know. So there's no need to go over that again and again. Okay, now another important thing. Another important property of R sorry, another important property of R is that R is an order field. So not only does R extend Q and allows us to operate within, make operations with Q that are completely consistent with their usual operations in Q. They're embedded into operations plus and multiplication, addition, and multiplication inside R. But also, the order structure of Q is preserved inside it, and it's actually extended to these new numbers that are in R but are not in Q. So this is a very important thing, because this is a different kind of structure that is not the one. I mean, it's not algebraic. It's not the algebraic structure that we had when we made compatible the operations of addition and multiplication. And we need this because that's what leads us to the most important new property of R. This allows us to talk about bounds, an upper and lower bounds. And with that in mind, so with this we can talk about bounds. And what will allow us to say that R is complete, which is something we haven't mentioned yet, but they actually call it here in the book as an axiom of completeness, because that's really what it is. As we learn more math, you will see that a complete metric space is a space where all Cauchy sequences are convergent. And this will be a consequence of the axiom that is referred to in other books as the axiom of supremum. I took the time to go over the construction of the real number so that it will not have to be an axiom. I mean, it's just something that we already proved that is the case for the particular construction of R we had. So every bounded set has a least upper bound, and that will allow us to say in the end that the real numbers are complete. So what is this property? So we'll just call it a property. And remember, this is a property that that is missing in Q, and it's actually the reason why we needed to define the real numbers. So we would have this property. So property of existence of supremum and infimum at the same time. Okay, so this is a property that is not present in Q, as we just said, and this is what it says. So every non-empty set of real numbers that is bounded above has a least upper bound. So Q, so the set of rational numbers doesn't have this property. It doesn't enjoy this. So very nice topological feature. Okay, so this is why we need to construct real numbers. And well, as a consequence of this, it's actually direct and is equivalent to this property that every non-empty set of real numbers that is bounded above has a least upper bound. We have something similar if you have a lower bound. So if similarly, so going back to the real number, so every subset of the real numbers that is bounded from below has a lower bound L with the property that if L prime, or let's use a different notation, then that if, say, C is another constant, C is a lower bound, say an possible, so a lower bound for the set, then L cannot be smaller than C. Okay, so this is what defines what's called an infimum. So these numbers here, the least upper bound and this kind of greatest lower bound, supremum and infimum. supremum and infimum. Okay, so these are the main objects of our attention for this will be the main objects of our attention for a while, and we'll be using them to do a number of things. One of them is to actually define the square root of 2, which was the starting point of the whole discussion surrounding the need for the real numbers. Okay, so this will happen then in the next few videos.